Hello everyone, how are you doing? Hope everyone is doing good. Welcome back to SMR Online Physics. I'm Mahesh. Today in this class, I will discuss about applications of total internal reflection. Like a few very common questions: how diamonds sparkle a lot, how mirage is formed, and what is the application of optical fibers and how do they exactly work out in real life communication purpose and various other uses. Alright, so today don't miss this class for sure, and if you're not sure about total internal reflection and the concept of critical angle, please check out my previous videos. The description will be provided in the link below. Right, here we go. Applications of total internal reflection. Yeah, you heard it right. If you're very new to this channel, then I need not tell you, but yes, please do subscribe my channel for latest videos coming up in the topics of physics. Alright, chalo aage badhte hain. Applications of total internal reflection. We will first of all discuss the first question: the sparkling brilliance of diamonds. Sparkling of diamonds. Now, from our previous classes, we definitely know that diamond is the most optically denser medium. Okay? If you remember, the optical density of diamond, you write Nd or you write mu d, is around 2.42. So since the optical density of diamond is so high, means I mean to say the refractive index of diamond is around 2.42, so light is going to slow down as it enters into a diamond crystal, right? So hence the critical angle of incidence for diamond is pretty low. It's around 24.2 degrees. Pretty low critical angle. So what happens is that because of the expertise of the diamond cutters, the diamonds are cut in a definite shape. Let me try to mimic a structure or mimic a shape of the diamond. Something like this. Something like this. Is all good? Okay. So the cut faces of the diamond are critical and very important to say for this phenomena to happen and for the sparkling brilliance of the diamond. So what happens is that if a ray of light is entering from air into diamond from any particular angle, once it enters in, and if the angle of incidence on one of its cut faces happens to be greater than 24.2 degrees, then the light is not going to pass out of it. Rather, now it's going to bounce from the surface multiple number of times before it leaves the diamond crystal. So I'm just trying to mimic what exactly happens in a diamond crystal. So this is called as multiple reflections, or we also call it in the physics language the total internal reflection happening, and that is why diamonds sparkle a lot. Hope I'm clear about this idea. Next, I'd like to talk about a very interesting phenomenon which we generally get to see on very hot summer afternoons. Technically speaking, it is called as mirage. So to give you a very common life example, let me just remind you, on very hot afternoons, if you ever come out of your houses and see the tar roads, for example, which is pretty common in the cities and towns, you'll see that far away on the tar roads there is a shimmering appearance, as if there is water which is sparkling around or which is reflecting the light into your eyes. And in search of that water, if you happen to go close by to that point, you find there is no water at all. It's absolutely dry, absolutely hot. That optical illusion is called mirage, as very common in hot summer days, particularly in deserts. It can create a beautiful optical illusion, and it's all because of total internal reflection of light, and along with that definitely refraction of light. So let us quickly discuss about how mirage is formed. How mirage is formed. What is the physics behind mirage formations? Okay, so what exactly can happen is that, let me try to draw a picture. Suppose this is the ground, that is the earth, this is the ground level, this is the earth around. Okay, so somewhere around, suppose you have a tall tree. Okay, not a beautiful one. Yeah, it serves the purpose. And somewhere around here we are standing around. So what exactly happens is that on a hot summer afternoon, the ground really gets heated up. This is really getting heated up. As it gets heated up, the air above this ground also becomes warmer. As it becomes warmer, hot air is always lighter, less denser. So as it is less denser, what happens is that the concept of refractive index comes into action. Please recall, refractive index of a medium also depends upon the temperature of the medium. So hot air, lighter air, hence the refractive index is also lesser. But what about the air above this? This is cold pockets of air comparatively. So this is your cold pockets of air, this is your warm air. Good. So cold pockets of air will have higher refractive index and warm pockets of air will have lower refractive index. So if you are seeing from top to bottom, the refractive index is continuously decreasing. If you see from top to bottom, the refractive index is decreasing. Alright, so as the refractive index is decreasing, and if there's a person who tries to see an object, the top view of that object, what can happen is that this light ray coming from the optically denser medium to the optically rarer medium, and if the angle of incidence near to the ground exceeds the critical angle of incidence, so along with the refraction there will be a total internal reflection, and hence the light rays reach to the observer's eye. So you can see that there's a huge amount of bent of light. Yes, absolutely. That is how these mirages are formed. So what exactly happened here? Let me quickly recap that. The hot air, the light rays coming from optically denser to the optically rarer medium, because you can see that the optical densities are not at all uniformly placed out. So it keeps on bending away from the normal, and if the angle of incidence exceeds near the ground above the critical angle of incidence, then you will find there is a total internal reflection and the light bounces off and gets into the observer's eyes. So what is the observer believing like? This is the light which comes from the top of the tree. So we always believe light travels in straight lines. So when I produce it straight down, yes, the person gets to see an equally tall tree which is inverted, is upside down. So there's an illusion, there is a tree which is inverted. But actually there isn't anything such like that. Okay? So this optical illusion is what is generally referred to as mirage. I get your point clear? Yes, hope so. So now I'm going to discuss about a modern technical tool, okay, which is very useful in modern day communication purpose to transmit audio and video signals to very long distances without much appreciable loss of intensity of the signal. Yes, you got me right. We are going to talk about the third very major application of total internal reflection, that is called optical fibers. So optical fibers are generally made up of very high quality glass or quartz fibers. It's been found that to very high appreciable quality of silica glass fibers, a signal could be transmitted to more than a distance of 1 kilometer without much loss in the energy of the signal. Alright? So what exactly is an optical fiber and how it exactly works out? Let me just explain to you. So every optical fiber looks like a cylindrical tunnel, a cylindrical pipe, so hence it can be also called as a light pipe, or you can also call it as a optical pipe. So every optical fiber will have two parts for sure. One is the outer part, which is generally called as the cladding, and the inner part is called as the core. So let me quickly do that. Yes, this outer part is called as cladding and this inner part is called as the core. So my dear, what exactly happens is, once the light enters into it at a certain angle of incidence, it is refractive index of the core being intentionally made larger than that of cladding, and if this angle of incidence exceeds the critical angle of incidence, the ray of light does not really transmit out, rather it bounces within the optical pipe multiple number of times, and as it bounces off multiple number of times, and this is what we call as total internal reflection. There is no loss of intensity, and even if the pipe is bent, there is no harm. The entire signal can be easily transmitted throughout the length of the pipe, and hence we may have the signal coming out of the other end, irrespective of the length. So without much loss in the intensity of the signal, a signal can be easily transmitted. So this is how an optical fiber or optical pipe actually works out on the phenomena of total internal reflection. Once again I repeat, the refractive index of the core is generally made higher than the refractive index of this cladding. So if the angle of incidence is greater than the critical angle of incidence, it undergoes multiple reflections within the fiber itself, and hence it comes out of the other end. So a bunch of optical fibers can be put to great use. It can be used for visualizing the internal organs of a body like esophagus, the stomach, or even the intestines. Alright? And at homes you might have really seen in the markets that a bunch of optical fibers placed upon a glass lamp and switch it on. You'll find that the light actually multiple times reflects off and comes out of the other end just like a tiny sparkling dot of light. That is how optical fibers actually work out. Hope I'm clear in this class about Mirage, the sparkling of diamonds, and how optical fibers actually work out. This is the applications of total internal reflection of light. Hope you enjoyed my class. So see you again on SMR Online Physics. Oh yes, don't forget to like, share and subscribe my channel if you really liked it up. Okay? Thank you. Have a good time.